Hi and welcome to another lesson about the x86 architecture. Today we are going to speak about basic arithmetic. Objectives of this lesson. You will learn about some simple arithmetic instructions. Those will be, for example, inc and dec, which are increase and decrease. Mul, which means multiplication, and div, which means division. You will get a feeling of working with x86 instructions. We are still not going to run any code, but don't worry, we are soon going to. Inc and dec. We are going to speak about those two instructions first. Those two instructions allow to increase or decrease numbers, only by 1. It looks like this: inc, destination, or dec, destination. This is the only argument of this instruction. Both of these instructions have only one argument, which is called destination. A wraparound occurs if the number is too large or too small. The wraparound, as usual, is according to the size of the argument. That means that we might invoke an inc or dec instruction, which might cause a wraparound, an overflow or an underflow of the number. For example, if we decrease a number which is already 0, then it is going to be the maximal number. It will turn into all ones, binary ones. And if we try to increase the largest number, then we are going to get back the number 0. Some examples. Inc EAX. This instruction increases EAX by 1. A bit of a different formulation. EAX plus 1 is stored into EAX. Another example. Decrease SI. This instruction decreases SI by 1. For another formulation you can see this. Some invalid example. We might try to increase a number, inc 1C5H. This is not going to work because 1C5H is just a literal, a constant. It is not a place. It cannot store any value, thus we cannot increase it. We can actually think about it and we can't answer the question, where will the result be stored? This is an invalid opcode. That means that we cannot decode any opcode to have this meaning. There is no such opcode. An example for the increase and decrease instructions. We assume that EAX begins with this value, FFFF, and it ends with E. We are going to see the effect of each instruction on the value of EAX. First, we begin with inc EAX, which is going to increase this value by 1. As expected, we get this result. Now we are going to increase AL. I remind you that AL is the lowest part of EAX, the lowest 8 bits, which are at this moment FF. We got a wraparound. FF plus 1 gives us 100 in base 16. However, as we work only with the lowest 8 bits, the wraparound occurred only in the lowest 8 bits and it stayed there. It didn't spread out to the rest of the bits. Now we are going to do the opposite, dec AL, and we get the original number. Now we are going to try to increase AX. I remind you that AX is half of EAX, the lowest half, which is 16 bits. It is made of these nibbles, F, 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 and F. We are going to increase it now. And similarly to the first case where we increased AL, here we increased AX, and we got a wraparound, but this time for 16 bits. Now we are going to do the opposite instruction, dec AX, and we get back the original number. This time we are going to increase EAX, which is the full register, which means everything, and we get 0 because of the wraparound. If we will increase it again, we are going to get 1, as expected. Those two instructions were mostly simple. Now we are going to look at some more interesting instructions. The first one is going to be mul. Mul allows to multiply numbers. Strictly speaking, we are talking about unsigned multiplication, which means that we multiply unsigned numbers. We don't look at the sign of the number. If you can recall, we have spoken in the past about the two's complement and numbers where the first bit determines the sign. So this time we are not going to consider these kind of numbers. We are only looking at unsigned numbers, which are the simple representation in base 2. It looks like this: mul and argument. It has only one argument. Surprisingly, we are going to soon see how could it work with only one argument, as we know that mul has to multiply two numbers. It has some forms. The first form is the very first one, historically speaking. It is going to happen if the argument is of size 8 bits. For example, if we chose some small argument like CH or CL or maybe AL or DL or DH, it performs this action. It takes AL, multiplies it by the argument, which could be any argument of size 8 bits, and it takes the result and stores it back into AX. I remind you that AL is of size 8 bits and AX is of size 16 bits. By the way, your processor has all the forms. I have a 64 bits processor made by Intel, x86 architecture. It supports all those three forms, the multiplication of 8 bits, 16 bits and 32 bits. We have those different forms mostly for backwards compatibility. Let us speak about the form of the 16 bits. Here, the argument is of size 16 bits, and we are going to multiply AX by this argument. This time the result is going to be inside DX AX. You might be wondering about this notation. This actually means that we are thinking about the number that we get by concatenating DX and AX, by putting them one next to each other. This number is actually of size 32 bits. In the days of 16 bits, we didn't have any register of size 32 bits. We could actually get something of size 32 bits by combining two different registers, DX and AX. Here we sometimes say that DX extends AX. The last form, which is more modern, is for arguments of size 32 bits. And this time we multiply EAX by the argument, and we get usually a large number, which is going to be stored inside EDX, EAX. This time the result is going to be stored in a place of 64 bits. Why is that? Because EAX is of size 32 bits and EDX is of size 32 bits. As usual, you should know that there is another form of 64 bits using the larger registers, but we are not going to speak about it now. An interesting thing to see here is that the size of the result is always larger than the size of the argument. If we say it exactly, it is twice the amount of bits. It is twice the size of the argument. And there is some logical explanation of that. Why is that? It makes sure that there is no wraparound. For example, here, AX times argument. Argument is of size 16 bits, and so is AX. So the result could be no more than 32 bits, which exactly fits into DX AX. For example, here, EAX times argument. EAX is of size 32 bits, and argument is also of size 32 bits. The result of the multiplication could be of size no more than 64 bits, which should fit in exactly here, into EDX, EAX. Some examples. Mul ECX. This multiplies EAX by ECX and stores the result inside EDX EAX. We can formulate it a bit differently, maybe more mathematically, something like this. EAX times ECX is stored inside EDX EAX. Another example, mul SI. This one multiplies AX by SI and stores the result inside DX AX. A different formulation, AX times SI is stored inside DX AX. Another example, mul AL. This one multiplies AL by AL. This is interesting. Actually, AL is in two different roles here. It is the implicit register that everything is multiplied with, and at the same time it is also the argument. So here we multiply AL by AL, and we store the result inside AX. As usual, we are going to consider some invalid example. We can look at this, mul 2AH. You might be wondering what is wrong with this example, because you might be thinking, well, this probably multiplies AL or maybe AX by this number, 2A, and stores the result somewhere. Well, you can't do this. There is no such opcode. And actually, there is no specific reason. Maybe because of some kind of historical limitation. Maybe in the past it was hard to produce such opcode. And the reality is that there is no such opcode. So you can't do this. You always have to move the number inside the register and only then multiply. Example for the mul instruction. We assume these initial values inside EDX, EAX, and ECX. We intentionally put EDX and EAX next to each other so you can see the full numbers here, because usually EDX extends EAX. We begin with the first instruction, mul ECX. This is going to multiply EAX by ECX and store the result inside EDX EAX. Take a look at it for a second. Indeed, we had 3 and 2, and we multiplied those two values. As a result, we got 6. EDX was zeroed because EDX is actually part of the result. This is the full result. The full result is of size 64 bits. Therefore, the instruction zeroed EDX. The next instruction is mul ECX. This is going again to multiply EAX by ECX. And as expected, we got C, which actually means 12. And we know that 2 times 6 is 12. We move on to a simple move instruction that just moves this number into AX, nothing very special. Now we are going to invoke this instruction, mul AX. This is actually going to multiply AX by AX. We got the result here. Actually, the full result is this one. It is composed of the lower part of EDX, which is DX, and this is AX. This is the full result. Another example for mul. Now we are going to multiply AL by CL. I remind you that AL is this number right now, 4, 4, and CL is 2. As expected, we got 88, of course in base 16. And the result this time is here, is marked in red. We just multiplied two values of size 8 bits, and we got as a result 16 bits. The lower part of EAX, which is AX, is of size 16 bits. Okay, this is a good time to take a break and come back when you are ready for the div instruction. See you again.